Hello everyone, welcome to the Essentials of Signal Processing, lecture number 2. The week's topic is the characterization of probably the most important class of signal processing systems, namely those that are linear and time invariant. For such LTI systems, the input-output relation can be written as the convolution of the input signal with the impulse response of the system. As a result, life becomes much easier because we can now describe LTI systems with just their impulse response, nothing else. Convolution is so fundamental to signal processing that it must be, unsurprisingly, the signal processing equation of the week. As a footnote, the systems covered in this course are discrete in time, and I also assume that the systems are causal, or that causality is irrelevant, because we are processing data already captured and stored in memory. For brevity, I'm not going to repeat the limitations to causal and discrete time systems as we go through the course, but I will highlight LTI on multiple occasions, as it is rather essential to the signal processing's operations that we are considering in this course. The learning goals for this week are the following. First, you're able to prove time invariance or linearity of a signal processing system given its input-output relation. Second, you can prove that a system is LTI by applying the superposition principle. Third, given the input-output relation of an LTI system, you can derive its impulse response and vice versa. Then fourth, you can rewrite any input-output relation of an LTI system as a time-discrete convolution. And finally, you can explain the properties of time-discrete convolution and actually do a convolution for short impulse responses and signals. In the Python exercises and assignments, you will calculate numerically convolutions over longer signals and longer impulse responses. Let us start with LTI properties. Some signal processing systems have an input-output relation that is linear. Others are time invariant, and some, for us the most important group, are both linear and time invariant. A system is time invariant if, roughly speaking, its behavior does not change over time. Inputting a signal xn at a certain time instance will give exactly the same response, the output signal, as if you would wait for a certain amount of time and then input x of n. The response y of n obtained is the same in both cases, but with a time shift. The way to formally prove this is to analyze the effect on the output signal when delaying the input over n naught samples. If the effect of this delay is that the response is an n naught samples delayed version of the original output signal, the system is time invariant. A famous example of a system that is not time invariant is our vocal tract. Because of the shape of our mouth, tongue and vocal cords, the input-output relation of this physical system varies over time. This is lucky, of course, otherwise speech would be impossible. However, if we consider short speech segments, then the vocal tract system can be approximated as being time invariant. This is why many speech and audio processing algorithms work with short, disjunct or overlapping time segments from 25 to maybe a few hundred milliseconds. A system is linear if a linear transformation of the input signal yields the same effect on the output signal. In other words, multiplying the amplitude of the input signal by a constant alpha will have the same effect of scaling the response signal by alpha. If you add two different input signals x1 and x2, you will get a response that is the sum of the outputs y1 and y2 associated to x1 and x2 respectively. The net effect of combining the homogeneity and additivity property leads to the superposition principle. As the word says, if you superimpose two scaled input signals x1 and x2, the system's response is the superposition of the two scaled output signals y1 and y2. Proving a system is linear is equivalent to showing that the superposition principle holds. Here is how you show that a system is linear using the superposition principle. At the top, we scale two different inputs x1 and x2 with arbitrary constants alpha and beta and add them. We then calculate output yn resulting from these superimposed inputs. At the bottom, we first calculate the outputs y1 and y2 and then scale with the same constants alpha and beta and add. If the results of the two sides are identical, then you have proven that the superposition principle holds, and so the system is linear. An important consequence of LTI is that in processing signals we are allowed to first decompose the input signal in any way we want. For example, into a sum of unit impulses or a sum of sinusoidal waveforms. We then process the components independently and finally add the results. This will give the same output signal as if we had applied the input-output equation directly to the complete non-decomposed signal. As we saw last week, many systems are described by this filter equation. It's not difficult to show that systems described by such equation are indeed LTI for any value of m and b sub k. Let us now consider this filter equation in more detail and work with the superposition principle. To that end, we decompose the input signal into an infinite sum of scaled unit impulses, as we saw in lecture 1. We then take one of these unit impulses, for instance at n is 0, and pass it through the LTI filter equation. What will happen? What will be the output signal in this case? Well, the derivation speaks for itself. If we compute y of n for n is 0, n is 1, n is 2 and so on, we get as output values the filter coefficients b sub k that serve as weights of the delayed samples x n minus k in the filter equation. So inputting a single unit impulse gives a system response that is equal to the sequence of filter coefficients. Since we are looking at the response of the LTI system to an impulse, we call this sequence the impulse response. The impulse response is a standard way to characterize LTI systems, and it has even received its own symbol, h of k. For the filter in question, we have h of k being equal to the b sub k's. Otherwise LTI systems, not described by this particular filter equation, can also be characterized by their impulse response. We can now rewrite the filter equation as shown here. The resulting equation, known as the convolution sum, or for the continuous world convolution integral, appears in many different science and engineering problems. The convolution is used so often that it even has been given its own symbol, the convolution operator. Please do not confuse this star symbol with normal multiplication. Convolution is quite a different operation than multiplication. In practical applications, the impulse response h of k may have many non-zero values, for example in the same order as the number of samples n in the input signal. The complexity of convolution will then be n squared. We will see in lecture 7 that the use of discrete Fourier transforms makes it possible to compute convolutions in a much smaller n log n complexity. Computing convolutions by hand can be a bit cumbersome. Nevertheless, it is good to practice this yourself, if only to be able to check the correctness of your software implementation or the correct use of convolution libraries. The easiest way is to multiply the convolution coefficients h of k with the input signal shifted over k samples and then add the partial results, as shown in this small animated example. It is essential that you realize that this way of calculating the convolution fundamentally makes use of the superposition principle. The convolution operator and impulse response have several properties that you should be aware of. Many of these properties should not surprise you, like impulse responses can be of infinite length, they can be non-causal, the role of hn and xn are interchangeable in the convolution sum, convolution is linear, time invariant, of course, commutative and associative. Slightly more surprising is that if you concatenate two LTI filters having impulse responses h1 and h2, the overall response turns out to be equal to the convolution of the two individual impulse responses. We conclude this second essentials with two exercises that we will solve during the online sessions. It is a good idea to first try to solve these two yourselves. More exercises are available through Brightspace. First, given an input-output relation, such as these, you must be able to prove or disprove that the system is linear using the superposition principle. For the proof, you have to go through the steps discussed earlier in this video. To prove that the system is not linear, you may also try to find one counterexample. I recommend you to try both approaches in the 3 cases shown here. Secondly, unsurprisingly, you should be able to determine the impulse response based on a given input-output relation. Consider for instance this input-output relation. What is h of n? And if x of n is then given as shown here, you should be able to calculate the convolution of hn and xn by hand. This week the mandatory Python assignments start. The second assignment is interesting because you cannot explain the observed phenomena yet, but you can at the end of the course. The third assignment refers back to an example in the first lecture, namely how to determine the optimal speech and audio prediction coefficients for so-called differential compression. That particular signal processing algorithm is at the very heart of speech compression in today's mobile communications. I wish you the best of luck and hopefully some fun with coding the signal processing algorithms. See you soon again!